All right, so we're moving on to near the last topic in the unit number 1 for grade 12 chemistry, the quantum model of the atom. We're going to try to take what we've learned and apply it to the periodic table. We're going to look at something called periodic trends. So we have several properties, and we're going to examine trends, patterns in those properties as they appear on the periodic table. The periodic table gets its name periodic because periodicity refers to similarities in behavior or reactivity due to the valence electron configurations of the elements. For example, alkali metals have one unpaired electron in their valence level. They all end in a S1 electron configuration. Because of that, they tend to have similar chemical behavior. For example, you should know from grade 11 chemistry that if you drop alkali metals, lithium, sodium, potassium, etc., into water, they explode in the water. They react producing hydrogen gas and explode. The halogens, the group near the right-hand side of the table, fluorine, chlorine, bromine, and iodine, they have 7 valence electrons. They tend to gain 1 during chemical reactions, and they behave very similarly also. The noble gases, with the exception of helium, which has 2 valence electrons, all of the other noble gases, neon, argon, krypton, xenon, radon, they've got 8 valence electrons. Their S and their P subshells are filled, and therefore they're exceptionally stable. They don't chemically react really. What we're going to do is look at 3 different trends among the different elements on the periodic table. We'll start with looking at atomic radius, which is exactly as it sounds. We're going to look at the pattern and the sizes of atoms. We'll look at something called the first ionization energies, and then we'll look at electronegativity. In grade 12 chemistry, we will not be looking at electron affinity, so you don't have to include that in your notes. Feel free to pause the video at any point to get caught up in writing or to listen to something again. So the first periodic trend that we're going to look at is atomic radius, the size of atoms. If we think of an atom here as being essentially a sphere with the nucleus at the center and the electron cloud, all of the orbitals overlapping, they would look sort of spherical if you just looked from the outside. So imagine we're an atom shaped like a sphere. Then the atomic radius is simply the radius of that sphere. This shows us the S block, so the first 2 columns, hydrogen down to cesium and beryllium down to barium. That's the S block on the periodic table. And then it shows us the P block also. So it's left out the D block and the F block just for simplicity. What I want you to do is just, in your own words, describe the trend in atomic radius that you see within a group. In other words, within a column on the periodic table, as you go down that column, what happens to the atomic radius? As you go across a period also, so that's the second trend. So you're going to describe what happens as you go down a group and as you go from left to right across a period. Make sure you know what those 2 words mean. A group is a column on the periodic table. A period is a row on the periodic table. So pause the video and just quickly describe the trend that you see. What happens to the atomic radius within a group? What happens within a period? Hopefully you agreed with this basic statement. So within a group, the atomic radii get larger. They increase. And when you go across a period from left to right, the atomic radii decrease. They get smaller. Okay? Now what you need to know, in addition to describing the actual trend, you need to have an understanding of why that happens. So let's start with looking at within a group. And again, feel free to pause the video to catch up in the notes as we go. So within a group, as we go down a column on the periodic table, and for discussion, why don't we take group number 1, so hydrogen, lithium, sodium, etc. for discussion. So we know that the valence electron for hydrogen is in the 1s orbital. In lithium's case, it's 2s1. Sodium ends in 3s1, and potassium ends in 4s1, etc. So as you go down that group, the principal quantum number, the value for n of the outermost energy level, increases. So n, the valence electrons, is found in level 1, 1s, then it's to 2s, then to 3s, etc. Electrons that are in valence shells have greater probabilities of being farther from the nucleus as you go down that group. So since the 1s is a smaller orbital than 2s, and 2s is smaller than 3s, etc. So the valence electrons are getting further and further from the nucleus. Because the valence electrons are further and further from the nucleus, the radii of the atoms increase. That's a pretty simple idea. I hope you agree. And folks, feel free to put this in your own words if you like, right? So what we basically just said was when you go down the group on the periodic table, valence electrons are found in higher and higher energy levels. Therefore, the valence orbitals get larger and larger, and therefore the radius of the atom gets larger and larger. What about when you go across a period? If you go across a row, and for discussion's sake, why don't we go from lithium to beryllium to boron across to neon? So we'll talk about period number 2 for this discussion. When you go from left to right across the periodic table, the first thing you'd want to note is that the valence electrons are found in the same energy level. So across period 2, we're talking about level 2. So the 2s and the 2p is being filled. Then what is changing if you're not changing the valence energy level? Well, what is changing is in the nucleus. You've got one more proton as you go across the periodic table in each element. So lithium has 3 protons, beryllium has 1 more, 4 protons, boron has 1 more, 5 protons, etc. So when you go across the periodic table, there's more and more positive charge in the nucleus. So the effective nuclear charge, the charge within the nucleus, gets larger and larger. It's more and more positive. If you've got greater and greater positive charge in the nucleus, that's going to pull on the valence electrons with greater and greater force. So therefore, the valence electrons get pulled closer and closer to the nucleus as you go across the row. So by the time you get to neon in row 2, there are so many protons in the nucleus in neon that the valence electrons have been pulled closer and closer to the nucleus. So neon is the smallest atom in row 2. Right? So when you go across the period, you always start with an alkali metal, which is the largest radius in that period, and by the time you reach a noble gas element, you've reached the smallest radius within the period. And it's because the nuclear charge increases while the valence electrons are found in the same principal energy level. So again, pause the video if you need to get caught up on the writing. Can you see in this graph what we just talked about? See if you can pause the video and see in this graph a graph of atomic radius on the y-axis and atomic number on the x-axis. Can you see that as you go down a group, the radius gets larger, and as you go across a period, the radius gets smaller? Pause the video and see if you can tell that by looking at the graph. So let's take a look, just for discussion's sake, at hydrogen, which is way over here on the left. Okay, so here's hydrogen. Then as we go down group number 1, hydrogen to lithium, to sodium, to potassium, etc., you'll notice that the radius is getting larger and larger and larger. When you go down the noble gas group, because they are also labeled on this graph, helium to neon to argon to krypton, you see also an increase. And we're picking those 2 groups just because they're labeled clearly on the graph. Now, what about within a period? Can we see within a period on this graph that the radii generally decrease? Well, if we take period number 2, that would start with lithium, and it would go down to neon. So as we start with lithium over here, and go from lithium to beryllium, beryllium would be here, and then keep going across that period, you end with neon over here. So from lithium down to across to neon, the radii are getting smaller. Now, if you do look a little bit on the right, you'll notice that there are some exceptions. Like over here, there's a sudden little increase in radius, and same thing here. We're not going to worry about those exceptions. If you looked closely at the graph, you'd notice that in this section, we're getting into the D block and even into the F block later on. We're only going to be considering the trends in a period across the S and the P block. So that would be from here to about here, okay? That's where we're looking at. There's a decrease in radius, and then we end with krypton over here. So generally, the trend is to decrease when you go across a period. All right, the second property is a little bit less intuitive. It's less obvious in terms of what it means. So be sure you've got a good sense of what this means before you try to describe the trend. So we're going to look at first ionization energy as a trend on the periodic table. The first ionization energy is the energy that you need to remove the first valence electron from a neutral ground state atom, and technically it should be in the gaseous state. So you have an atom in the gas phase, it's neutral, it's not an ion, and you're going to take away a valence electron from that atom. The energy you need to take away the electron is called the first ionization energy. So for example, here we have a neutral magnesium atom. If we take away one valence electron, we have Mg positive as a result. The ionization energy, number 1, the first ionization energy for magnesium, is 738 joules per mole. So if you wanted to do that for 1 mole of magnesium atoms, you'd need 738 joules of energy. If you looked at the electron configurations, you're taking magnesium atom, which ends with 3s2, and you're converting it to 3s1. You're taking away 1 valence electron. Now, of course, you don't have to stop at 1. You could reach in and take out a second valence electron, and then a third and a fourth. You could take away all the valence electrons and then keep taking away more electrons after that. So there's a second ionization energy, a third, a fourth, until you run out of electrons. One thing you'll want to note, and we're going to come back to this later, is that the second ionization energy, the third, the fourth, increase. So the first ionization energy is always the smallest for an atom, and as you keep taking away electrons from that atom, it gets harder and harder. So the ionization energies get larger. So for this discussion now, we're only going to focus on the first ionization energies. So here's a graph that shows us the first ionization energies for elements from hydrogen all the way across the periodic table. See if you can pause the video and describe a trend the same way we did on the earlier graph within a group. So from top to bottom within a group on the periodic table, and then within a period, the same way we did radius, from left to right across a period. So pause the video and see if you can see that within this graph. So if you located hydrogen, hydrogen would be over here, and hydrogen to lithium, which is here, to sodium, to potassium, to rubidium, we're going down the first group on the periodic table. It's not a huge change, but if you do look at it closely, you'd agree that there's a decrease in the ionization energies. Similarly, if you go from helium, the top of the noble gas family, down to neon, to argon, to krypton to xenon to radon, there's a more clear decrease in first ionization energy. So when you go down a family, we know that atoms get larger, but now we see that the first ionization energies get smaller. What about within a period? Well, let's find a period on this table. Here's lithium, which is the start of period number 2, and neon is at the end of period number 2. And there's a couple of blips along the way, but basically as you go from lithium to neon, the general trend is to increase in first ionization energy. So the price you need to pay to take away the valence electron gets higher and higher as you go across the row. It gets harder to take away valence electrons when you move across the table. Similarly, here's sodium, and across to argon. When you go across period number 3, there's a general increase also. Now in AP chemistry or college chemistry, you would discuss and explain those little blips along the way. In grade 12 chemistry, we're just going to focus on the general trend, which is to increase across a period. So now let's try to explain those trends. So again, pause the video as you need to write down the notes. So the trend, as we saw when you go across the period, was to increase. Now, if this was AP chemistry, we would focus on exceptions, those little blips. We're not going to do that in grade 12 chemistry. Now, why would you see an increase in first ionization energy across a period? Well, remember we said when we discussed the radius of atoms that the valence electrons were in the same shell. They're in the same energy level. So when you go from lithium across to neon, all the valence electrons are in level 2, 2s and 2p. When you go from sodium across to argon, the valence electrons are all in level 3, 3s and 3p, etc. So, given that, we also remember that when you go across the row, the number of protons in the nucleus increases. The nuclear charge gets larger and larger, more and more positive, because of the protons increasing across the row. If you have greater nuclear charge, we said earlier with radius that that would pull the valence electrons closer. Well, if there's greater charge, does it make sense that it's also going to be harder and harder to remove the valence electron because it's got a greater and greater attraction to the nucleus? So when you go across the period, the increased nuclear charge makes it harder to remove, so the first ionization energy goes up and up. Now, what about the group? If you understood the connection a moment ago to radius, then this will also make sense. We know that the nuclear charge within a group also increases. There's more and more protons when you go down a group. So you might think that that would make the electrons, the valence electrons, harder to remove. But the difference here is that the valence electrons are found in higher and higher energy levels. So because the valence electrons are in higher energy levels as you go down a group, they're further from the nucleus. That makes the attraction smaller as you go down the family. The other thing to consider is that the outer electrons are always shielded, partly, from the nuclear charge by inner electrons. So if your valence electron is 3s1, you are shielded from the nucleus of the atom by the electrons in 1s and the electrons in 2s and 2p. So the outer valence electron doesn't feel the full nuclear charge. Therefore, as you go down the family, primarily because of the increased distance from the nucleus, the valence electrons are easier to remove and the ionization energy decreases. Just to connect back to grade 11 chemistry, you might remember seeing a video of the alkali metals being dropped in water. As you went down the family, the explosiveness of the reaction increased. That's because when you went down the family from lithium to sodium all the way down to cesium, I think in the video you watched, the outer electrons are easier and easier to remove. So the reaction becomes more and more explosive when you go down the family. So first ionization energies increase within a period because the valence electrons are in the same energy level, but there's more and more nuclear charge. When you go down a family, the ionization energy decreases because primarily the outer electrons are further and further from the nucleus, and they're shielded from nuclear charge as well. Okay, we're going to skip this. These are the exceptions within a period. So if you see this in your printed notes, you can just draw a line through this. In grade 12 chemistry, we won't worry about the exceptions. Electronegativity. This is the third and final periodic trend that we're going to consider. We're going to come back and talk more about electronegativity as the final topic in this unit, but for now let's just focus on it as a periodic trend. If you have your data booklets, there is a table right after the periodic table in the data booklet. It looks like a periodic table, but it's called the table of electronegativity values. So you might want to take a look at that as we discuss this. Electronegativity it's a little bit of a strange sounding word, but it's basically a measure of the attraction that an atom has for electrons within a chemical bond. So if two atoms are in a chemical bond, they're sharing some electrons, the attraction that an atom has for the electrons it's sharing with another atom, that attraction is measured by electronegativity. So if you have a high electronegativity, the atom will attract the electrons very strongly within the bond. A low electronegativity, it attracts very weakly the electrons within a bond. Okay, now there's a data table in your booklet, but we'll see one here as well. Here's a graph that shows electronegativity trends. Can you see a trend within a period? Can you see a trend within a group? Pause the video and see if you can identify a trend within a group, a trend within a period. Okay, so within a group, if you said here's hydrogen, lithium, sodium, potassium, it looks like within a group electronegativities are getting smaller. Fluorine, chlorine, and then going across, I guess that's krypton, so this would be bromine here. Okay, so those are the halogens. So again, as you go down a family, the electronegativities are getting smaller. What about when you go across a period? Well, here's lithium, and here's fluorine. That's sort of across period number 2. And you might be wondering, where's neon? Neon doesn't form chemical bonds. Neon and helium and argon, they never form chemical bonds, those 3 noble gases, so they're not shown here. You might have been told in grade 11 chemistry that all noble gases don't react, but in fact, when you go down the family, krypton and xenon and radon, they can form a few compounds, not many, so they're showing up on this graph as with having an electronegativity value. So essentially, as you go across a period, the electronegativities are increasing. As you go down a group, they're decreasing. This trend you don't really have to memorize because you'll have your data booklet with you during a test or exam, and a table like this will be available with electronegativity values. So hydrogen's electronegativity value is 2.1 units. And as you go down the first column, you can see the electronegativity is decreasing. The halogens at the other end, fluorine, has the highest electronegativity of all the elements. And as you go down the halogen family, fluorine, chlorine, bromine, you see a decrease in electronegativity. So there's the 2 trends. When you go down a family, there's a decrease. When you go across a period, there's an increase. Now, we're not going to explain the trends for electronegativity. We're going to just leave it as know them. And partly that's because you have this table in your data booklet. All right, so that's it for periodic trends. We've looked at the trend in radius of atoms, first ionization energy, and electronegativity. Be sure that you're able for each of them to define the property, so you should know what atomic radius means, you should know what first ionization energy means, and what electronegativity means. You should also be able to state the trend within a group and within a period on the periodic table. And for the first two properties, the radius and the ionization energy, you should be able to explain the trend within a group or within a period. Okay, so on a test, you must be able to define the property, state the trends within a group and period, and for the first two, explain the trends. All right, we'll leave it there.